So there are some basic characteristics and some information we need to cover before we get more into the Zeners today. So let's look at what we have here. The first thing, we've been talking about regular diodes so far. And we all know that regular diodes work in what direction? Forward or reverse?
You said what position do normal diodes work in?
Yeah, a regular diode, just a regular diode that we've covered so far. How does it work?
Forward,
Forward bias. And what is the voltage drop across that diode?
0.7.
0.7, excellent. So here, in our first part right here, we see that in the forward bias, all right, the Zener diode acts like a regular diode. So in forward bias for our Zener, it's going to act just like the diodes we've covered so far in our class. And it's going to drop that 0.7 volts. So keep that in mind when we start looking at clippers and stuff, you know, how we set these up. Okay, so, but I've told you before, unlike a regular diode, our Zener diodes work in reverse bias. They work in reverse bias. So in this case, if we tried to work a diode or run a diode in reverse bias for a regular diode, what would happen?
Would it short out?
Okay, or what is it called? We would
An
get
open
to
and an open.
it would, well, we'd have to get to a certain voltage, right? What would that voltage be approximately?
Isn't it 50 volts?
50 volts, very good. So it'd be about 50 volts, excellent. So, and then that's basically where it would break down, okay? Now, in the Zener here, it actually works and operates in that region, okay, in that region. Also, Zener diodes would break down voltages here that are less than approximately 5 volts, operate predominantly in the Zener breakdown region. And we're going to see this here in just a second on what it looks like in the graph. Also, Zener diodes here with voltages that are greater than 5 volts normally operate in the avalanche region. This is a rapid buildup of conduction electrons. Kind of like the same thing, except that like in a regular diode, we have that forward bias. And once it gets to that approximately 0.7, then all of a sudden, bam, it takes off and we have a lot of current flow, okay? So same way with the Zener, except that it's working in reverse bias in that avalanche region. Okay, the last part here is the Zener diodes are commercially available, of course, breakdown voltages less than 1 volt, all the way up to 250 volts, okay, with tolerances from 1 to 20%, okay, from 1 to 20%. Now, you will need to know some of this stuff here when it comes to test time, so please make sure you take notes or whatever and review this, and this will help you prepare for the test that's coming. All right, any questions on this part right here? It's just some information that we need to cover so that you get a better understanding of Zener diodes.
Yeah, I'm just trying to get it all down.
Okay, yeah, go ahead, man. If you want to get it down, go ahead. All right, so here we have our Zener breakdown characteristics curves. Now, you will absolutely need to know these characteristics curves and this breakdown information. You will, I'm telling you now, you will see something like this on the test. So please make sure that you understand everything that's happening here. So we're going to go through this and you guys can get this down if you need to, that's fine. So here we have on the left side, we have our characteristics curve that looks very similar to our regular diode characteristics curve. If you remember on our regular diode characteristics curve, we had this breakover point here with about 0.7 volts, and then our conduction just took off, right? That's the regular diode. Now, this is a Zener diode. It works the same way in forward bias. So in forward bias, there is no change whatsoever compared to a regular diode. But this diode, Zener diode, works in reverse bias. So when we get to our breakdown voltage here, all right, or break over voltage at VZ, our Zener voltage, then it's going to start conducting. This is what we call the normal operating region. So between here and here, usually in a regular diode, we have our destruction of the diode. But with the Zener, this is where it's actually working. Okay, this is in the reverse bias part of the diode. Now on this side over here, we have our breakdown for our characteristics curve as far as how does a Zener actually work and what areas do we need to be concerned with. So this first area right here, this is referred to as our knee current for the Zener. This is our knee current for the Zener. And that is basically right here at this point where it just starts to break over. Right after the current, right after it broke over at here, we start to break into our knee current. Then we have our test current. Okay, and all these are going to be figured into your calculations when we start looking at the formulas on how to calculate minimum and maximum voltage for our Zener. Then we have our maximum current for a particular Zener. So we do have our knee current, which is the beginning where it breaks over. We have our test current right here, which most of this stuff is given to us on the spec sheet. And then we have our maximum Zener current of how much current we can actually have going through the Zener before it is no longer working properly. So we have 3 areas to be concerned with. You need to make sure that you know how to draw both of these, okay, and label them. So make sure you understand what's happening in each one of these. Does anybody have any questions on these characteristic curves? Okay. All right, so let's move on to the symbols. All right, so we have 2 Zener diode symbols. All right, we have 2 different symbols. We have one on the left-hand side is our ideal or first approximation. This is the approximation that we're going to be using in class, okay, for our calculations. And then we also have a practical or second approximation. So for your sake, you just need to know how to draw these symbols and how to identify the difference between the two. What is the only difference between the two and just looking at them? Can anybody tell me?
One has a resistor inside the
Very good.
diode.
Excellent. Good job, Logan. So there's just an internal, we're showing an internal resistance, okay, which on our spec sheet would be referred to as ZZ, okay? And we're gonna look at a spec sheet here in just a second. All right, so these are the two, but we will be focused on the ideal or first approximation. Just know that you need to identify both of these on your test, all right? And of course, when you're working for someone.
As in like, we just need to draw them.
Yes, you need to, just
Okay.
like you see it right here. That's all you need to do. All right, does anybody have any questions regarding these two symbols for our Zener diodes? All right, please give me a quick thumbs up if you have these down so we can get on to our calculations. Excellent. Thank you. Thank you. All right. Thanks, Sam, Tess, Theo, Isaac, Dylan, Brett, Artem. Excellent. Micaiah, thank you. Okay. All right. So let's move on and let's get into our calculations. We are going to do several calculations just to make sure that you understand how to calculate the minimum and maximum voltages for our Zener. Now, please understand, does anybody remember what we talked about earlier in the semester regarding Zeners? What is the function of a Zener? We talked about this when we talked about power supplies. Can anybody tell me?
I do not remember.
Okay, no problem.
I don't think I was there for that one.
Okay, all right, no problem. Okay, so the purpose of a Zener is for us to be able to regulate a DC voltage. All right, remember, if you remember in our power supplies, you saw that you had the power supply breakdown and you got all the way down to the right-hand side, the far right on your block diagram. And we wanted to get that nice, steady DC output, right? The Zener is what is going to help us control that DC output to give us a nice, steady output. So that's the purpose of a Zener. And Zeners are extremely important because when you think about systems like computer systems, for instance, we need to have a fixed, steady value regardless of the change that we have in input voltage. We need to make sure that we can keep a steady output. That's why there are so many different Zener diodes with different specs, because they all are regulated at different values. And we're going to look at that in these examples here and how we can calculate what kind of change in voltage that we can have on a particular Zener. Now, this is where you're going to need that spec sheet. So it's either you can look in your book on page 108, or you can actually look at it online. I've uploaded it into the week 8 folder. So please have that available when we go through these. I'm going to start drawing out the first one, and we're going to walk through it and then give you guys a chance to do some of the others.
Is VZ at IZ just VZ?
VC at IC, where you, VC
At IZ,
oh,
like in,
IZM?
no, in the spec sheets, it says like where it says
Oh, yeah.
minimum type and max, and it says VZV at IZ. Is that just VZ?
No, yeah, so give me 1 second, Logan, I'm gonna walk through all that.
Okay.
Yeah. All right, get this down real quick, and then we're gonna start going through this step by step. All right, give me a thumbs up when you have this down, please. All right, thanks, Artem. Thanks, Dylan. Thanks, Isaac. All right, thanks, Logan. Thanks, Sam. Thanks, Theo. Thanks, Tess. Thanks, Micaiah. Oh, sorry, guys. Forgot to put the resistance value on here. Thanks, Brett. The resistor is 470 ohms. So throw it down there real quick. Okay. All right, so the first thing we're going to look at is, you guys should have this down already, the information regarding the spec sheet. Okay, the information regarding the spec sheet, which in this case right here, we're looking at the VZ, the PD, and the IZK. The VZ is our Zener voltage, the PD is our dissipated power, and the IZK is our knee current. So let's take a look. I'm going to switch over my screen and share my spec sheet so that we can go through that and show you what you're looking for. The first thing we need to look at is, you wrote this down already. We have a Zener diode with a part number of 1N4744A. Okay, 1N4744A. Now we don't see that here, right? The last one we see here is actually 42. So what we're going to do is we're going to scroll down a little bit to our next page, which is right here. And we're going to look up this information, the 4744A, which in this case right here, 4744A is this one. Right? Now we wanted to know, what is our VZ? Okay, what is our VZ in this case with IZ? Now, we want to know, if you notice on there, we need to know what is it typical? What is our typical value for our VZ from our spec sheet, which in this case is going to be 15 volts. So our VC, when we write this information down on our question here that we're trying to solve, we need to write 15 volts because this is our typical voltage for this Zener, for this particular Zener diode. The next thing we have is our IZK, okay, our IZK. So with this one, we just follow it straight on over until we get to IZK, which is rated in milliamps. And we can see that this value right here is actually 0.25 milliamps. This is where we get our value for IZK that we need from the spec sheet in order to calculate our minimum and maximum values for our input. All right. So this is where this is. Now we need to find out what is our PD, or our power dissipated. So we go back up to the top sheet up here, and we can see that our PD is right here. We follow this over to our value of what it is. This is for all these diodes, Zener diodes, and it's a value of 1 watt. Okay, power rated in watts. So we have a value of 1 watt for every one of these Zener diodes that we look at. Now, you'll have this exact spec sheet. This is the one I put online, and you'll also have it. The book also uses the exact same spec sheets that we use right here. So if you have your book, you'll notice that on page 108. Plus, I think in your book, they actually have a few more Zeners in that same area.
Come test day, we can be allowed to have our book.
No, well, don't worry about, you're going to get a handout. You don't have to memorize
Okay.
these.
Okay.
Yeah, I'm not going to make you do that. All right. So, this is the information right here, okay, for our, the parameters of our Zener diode for the top part. This affects all of them, okay? And you're going to see stuff in there asking you questions about the rate above 50 degrees Celsius. What's the value here? Basically, it's asking what kind of effect, or what is the nominal temperature for our Zener diode in order for it to work properly. So these are kind of questions that you might see in your homework assignment. So just keep that in mind whenever you do your homework assignment. All right, any questions on this, on where we find the information for our VZ typical and for our IZK? These are the 3 things, and the PD, of course. These are the 3 things that you're going to need to know in order to do your calculations for these upcoming questions. So make sure you understand that. I'm going to give you a specific number for a Zener, and you're going to have to look it up and fill in the information for the spec sheet. Of course, we're going to do that here on this first one, for example. In this first one, this first example right here, we had our model number for our Zener diode was the 1N4744A. And that 1N4744A had a Zener voltage of 15 volts. That is the typical. It had a power dissipation of 1 watt, and it had that IZK of 0.25 milliamps. So those are the 3 primary things we need in order to start doing our calculations. The first thing we need to do is we need to go ahead and calculate our IZM. In other words, what is our max current for the Zener? And the way we do that is we take our power dissipated, which in this case was right here, and we have that as 1 watt. And we're going to divide that by our VZ, which was our 15 volts that we also received from our spec sheet. And we're going to come up with our value of 66.67 milliamps. All right. Anybody not see where we got this? Let me know now before we continue. If you have questions. All right. Excellent. Thank you, Logan. All right. So now that we have that, we're going to go ahead and start looking at our maximum input. Our maximum input voltage. So here's how we do that. In our formula, we have IZM times R. IZM we just calculated. So that's going to be our 66.67 milliamps times our resistance value, which in this case is 470 ohms. And that is going to give us a value of 31.33 volts. All right, so 31.33 volts. This is our voltage, max current across the resistor. Now that we have that, we already have our VR at IZM, which in this case, for our VN max, we have 31.33 volts plus our VZ. Our VZ was given to us again over here, which was 15 volts. So if we add those together, we come up with 46.33 volts. So for our max input voltage for this particular Zener diode, we have a value of 46.33 volts. So now we have half of it figured out. Now we need to figure out what is our minimum input voltage. In this case, we have IZK, which is right here. IZK we got from the spec sheet, which was our 0.25 milliamps. So we're going to have 0.25 milliamps times our resistor, which was 470 ohms. And that is going to equal 117.5 millivolts. Now that we have our 117.5 millivolts, we can come down to our VN minimum and go ahead and bring that 117 down for VR. And add that again together again with the VZ, which is our typical voltage for that Zener, which is 15 volts. And that is going to give us 15.12 volts. So our minimum that we can have for this Zener to actually conduct properly is going to be 15.12 volts. Now, what I want you to notice is the range. We can go down to 15, as low as 15.12 volts, and as high as 46.33 volts on our input voltage. Now, what does that mean for us? Our output, which is here across our Zener, is going to be approximately what voltage between that range of 15.12 and 46.33? What is the range? What is the output going to be? Any ideas?
Would it be 31.2 to 21?
Nope.
No.
Okay, think about what we said about a Zener. What is the whole purpose of a Zener?
To regulate DC voltage and output as in the output.
Okay, so regulate DC voltage, correct. So what am I looking at here then for an output? Approximately what value? Any idea? Somebody else started to say something.
It works in the breakdown region.
Okay, it works in the breakdown region, but what value of voltage are we looking at? Theo, do you have an idea?
I was thinking about the diode voltage of the 0.7.
Yeah, so that would be in forward bias.
Yeah. And then, yeah.
So let's look at this for a second. How do we know that this is in reverse bias? Who can tell me how you know that this is in reverse bias?
Is the DC source positive is going to the cathode?
Excellent. Nice work. We got our positive here, and the positive is going to our cathode, which is opposite, right, for a regular diode. So we
Mhm.
know that this is wired correctly because it does work in reverse bias. All right. So let's think about this for a second. The purpose of a Zener diode is to regulate a nice steady voltage with fluctuations in our input voltage. What do you think our output is going to be approximately?
Would it be the average between the two?
Nope.
Does this have to do with that 50 volts? I think that someone mentioned earlier. It's in the diode that has to build. No.
Nope. Okay. So let's look at this. Look at our spec sheet for a second. What is this Zener diode rated at for VZ? Our typical voltage, what is it?
2.5
No.
or
15?
50. Oh, 15. I was looking at the
15, right?
Mhm.
15. Look, this is our rated, this one right here, our VZ, which is our Zener voltage. That's what it's rated at. So what we're saying is that because there are so many different Zener diodes available, we can choose one that we want to use for a particular value, right? So we want to be able to maintain that nice, constant, steady DC voltage, no matter what happens on our input. So if our input goes down to 15.12, or if it goes all the way up to 46.33 volts, guess what? We're going to maintain 15 volts approximately on our output. That's what a Zener does. It gives us a nice, steady, regulated voltage based on the spec sheet of that diode. Do you guys see this? Do you understand what's happening here?
Yes.
Okay. So what we're doing over here when we're thinking about the minimum and maximum, we're thinking about how much voltage or fluctuations in voltage can I actually have on the input of this Zener diode so that it still maintains a 15-volt regulation. And that's a pretty big range for our input for that Zener diode to maintain conduction in the reverse bias format. Does everyone see us? See, understand we always get spikes, or I'm sure you guys know this. You always get like spikes in your current. You see lights flicker sometimes or whatever. These are things that cause voltages to go up and down. And if we're trying to run something and it has to maintain that steady voltage, we don't want our power supply or whatever to shut off if it has a slight change or variation in the voltage that's coming in. This is the purpose of a Zener diode. It helps to regulate our voltage so that we can keep that nice steady DC output. Any questions on this before we go to the next one? You guys gonna do some calculations?
I had a question for when we're dealing with tolerances, I'm guessing in a more real world application, probably in the classroom, I'm assuming too. When we would specify V in minimum, V in maximum, would we specify the range given the tolerance if we know the tolerance?
Yeah, the tolerance now is going to be affected, is going to affect also the minimum and maximum values. Does that make sense?
Okay.
Yes. Okay, we're just talking about an ideal diode. So that's why we're not including the second approximation with the resistor in it. We're just looking at the regular diode, so which is basically in forward bias a 0.7 volt drop. But yes,
Okay.
that is a good question, Artem. That's exactly correct. All right, so let's go ahead and I'm gonna give you guys your first one here for you to calculate. And let's see how you do. All right, this Zener is going to be 1N4748A. And that's everything you need. Okay, so you're gonna be looking up on your spec sheet. You're gonna be looking for 1N4748A, and then you're gonna start filling out everything. So we wanna know what the spec sheet values are when you come up with those. We wanna know what IZM is going to be for our max current. And then also we wanna know what our minimum voltage and our maximum voltage is going to be, and also what our V out is approximately going to be. Okay, so when you get those, put those in the chat box, please. Send those to me like you did before. Oh, sorry, guys, hold on a second. I gotta change the resistor value. Hold on. Resistor is 330 ohms. All right, go for it. Awesome, Sam. Also, Sam, what's your V out going to be? That's the only thing you got left, Sam. Perfect. Excellent. Good job, Sam. Nice work.
For IZM, when we're doing that, is that gonna come out milliamps or millivolts?
No, so IZM. So I represents current.
Current, okay, current, okay.
Yep. All right, Brett. And Brett, what is the V out going to be? Perfect, Brett. Okay, Tess. Good job. Okay, so you got 2 parts down so far, Tess. Keep it going. All you really need, Tess, is the V out. What is V out going to be? Excellent. You got it, Tess. Good job. Okay, Micaiah, I think they're off because look at the spec sheet again. Double check your VZ value. Okay, double check your VZ value. And then recalculate. Artem, good job. Nice. Also, if anybody's having problems or they can't figure it out, please just put in the chat box, let me know.
I'm just a little confused, I guess, with my numbers because they're a little like different than last time. Like my maximum is smaller than my minimum, which doesn't make sense unless it's supposed to look like that.
You mean are you talking about input voltage?
Like for when it says V in min, V in max, the numbers I got like kind of like flip flopped unless it's supposed to. I mean, I can let you know what numbers I got to see if they're in the ballpark, but this doesn't make sense to me, I guess.
Yeah, let me see what numbers you got, Logan. Micaiah, VZ is 22. So go ahead and redo your calculation. Let's see what you come up with. Okay, no problem, Martin. We're going to go through it. So hang tight. Yeah, Logan, that's off. I'm not sure what values you came up with from the spec sheet. That's the next question. So if you want to put those in the chat, let me know what you come up with for your spec sheet values.
Okay.
Will we be doing another example after this?
Oh, yes, we will.
Okay, I'll copy and paste this.
I think I might be wrong about the PD, but that's like what I saw when I looked in the book.
No, those are all correct. Oh, just make sure your IZK now, that's 0.25 milliamps now, not just. Yeah, those are the right values, Logan. You just have to put them in the formulas. That's all. Don't worry, we're gonna go through it again. So
Yeah, because I don't. Maybe I'm doing something wrong because when I did the math for the maximum, like doing the PD over the VZ, and you get the milliamps, and I multiplied that by the resistor.
yeah, how much did you get for what did you get for your IZM?
I got.
Yes, that is correct. I mean, you could round that off to 2 places past the decimal, but yes.
Oh. Never mind. I'm writing him in the wrong spot.
Oh, okay.
Is this hold on? Is this right now?
Sorry, did you enter something already?
Sitting right now, typing it.
No, I'm still not sure where you're getting your VN that VN minimum and maximum. You got the right values. It's just when you multiply it times the 330 ohms.
I get.
And you did put milli, right? 45.
That's what I get when I multiply by 330.
Yeah, so that's because of the rounding, because you didn't carry out the 45.45. But
And then I add that to the VZ, and then that's what I get for the maximum.
So.
Or am I typing it wrong into you?
No, add that to VZ, and what do you get? Because the other one you're showing as 82.5. So.
Oh, I'm just not. Oh, so I'm just not typing it right to you then. Would that be
There
right?
you go. Much better.
Okay.
Now you can do the minimum. Okay, so all right, we're gonna go ahead and go through this real quick here. So you guys should have come up with, for your VZ, I think you guys all got the spec sheet correct, which was 22 volts. Your PD again was 1 watt, and your IZK was the 0.25 milliamps. We know that our VZ, or this Zener, is rated at 22 volts, so we know that our output is going to be approximately 22 volts. And then you did your calculations, and your V minimum should have been somewhere around 22.08 volts. And your maximum should have been around 37 volts. Does anybody not understand how we got this? Please ask me now.
I'm just trying to figure out how you got the 22.08 because I'm not getting that number.
Okay, so the 22.8, you got your IZK, right? Times R. What is IZK?
IZK is 0.25.
Okay, so 0.25 milli times 330. What do you get?
8.25.
82.5 millivolts, right? 82.5.
Mm-hmm.
Add that to 22.
104.5.
Wait, 82.5 milli plus 22. What do you get?
Oh, milli. Oh, mine is, it's not in milli, that's why. Okay, there it is, 22.08.
Perfect. There you go.
Okay.
So that's all you forgot was the milli.
Mm-hmm.
Okay, any questions? Anybody else before we go to the next one? Anybody not sure? All right, let's do the next one. All right, our resistor for this one is 1.2 k ohms. And our Zener model number 1N4738A. Okay, let's see what you come up with. Looking for V out, we're looking for V in minimum and V in maximum. Sam, double check your calculations again. I think you basically forgot something when you did your inputs. Double check it again for your minimum and maximum values. Tess, perfect. Nice work. Good job. All right, Artem, looks good except for your V out. I think you just looked at the wrong number. Double check that number again for V out. Ah, there we go. Good job. Brett, nice work. Perfectly done. Nice work. Yes, Sam, that is correct for VN max. That is correct. Your VN minimum though, double check that again. Logan, yes, that is that's close enough. I'm sure it's just your rounding, but yes, that is good for VN max. I'll take that.
All right. I think I do the minimum wrong, Mr. Parsons, but when you do it, do you take the 0.5 times 12 times the 1.2K, right?
Yep, and that gives me my first part. Yes.
And is that in is the 0.5 in milli, or is it just a 0.5?
No, that's 0.5 milli. That's what. they're
Okay,
saying.
okay.
Yeah. Yes, Logan, perfect. That is it for V in minimum. Now, what's your V out? That's all you need to know. That's it. You got it. Good job, Logan.
Perfect.
Okay, this is our last one, guys, for this. So make sure you got this down. Does anybody have any questions? Anybody stumped? Anybody not sure? Okay. All right, so let's look at this. So we should have come up with our V minimum on this one would have been 8.8 volts. And our maximum would have been around 154.54 volts. And then our spec sheet, we should have had 8.2 volts for our VZ. Again, our power is going to be rated at 1 watts because if you remember, that PD is for all the Zener diodes on that spec sheet. And then our knee current was the 0.5 milliamps. And then our V out, of course, is whatever our VZ is rated, our Zener is rated at, which was the 8.2 volts. And that is a approximate value. Does anybody have any questions before we do this last part?
Nope.
Okay. All right, so now we looked at clippers and clampers already. So with the Zeners, we're going to be looking at clippers or limiters. So let's take a look at what they would look like on an output waveform. So I'm going to draw the first one here. We'll do a few here real quick. These are already, you should be already familiar with. It's just that we're using a Zener diode this time instead of a regular diode. Okay. Whenever you think about the output waveform, you must remember that what are the rules for a Zener diode? How do they function? They work in what bias?
Reverse.
Reverse bias?
Reverse bias. And in forward bias, they act like
Diode.
a regular diode. A regular diode drops how much voltage?
0.7.
0.7. Okay, so the first thing we have here coming in is our positive peak, right? We have our positive here and our negative here. Positive there, negative there. Which one of these diodes, which one of these Zener diodes is working properly at this moment?
The bottom one,
And how do we know that?
because the way the positive is being felt on the resistor and the cathode is being felt on the diode.
I
I guess anode, the anode, sorry.
Yeah, the anode. There we go. Phew. All right. So the negative is on the anode right here, right? And technically that's reverse bias. So if this is reverse bias, and we're talking about the first positive pulse coming in, the current is going to be flowing in that direction, correct? It's going to be flowing upward, correct?
Yes.
If it's flowing upward, what do you think our output voltage is going to be?
$8.2.
All right, who said that?
Brett did.
Brett. All right, excellent. 8.2. And so, in other words, this output is going to be doing what at a certain point?
Flat,
Charging.
leveling.
Flat, that's right. It's going to clip, right? Or limit. And then it's going to go back down, and we're going to be looking at the other part. So remember, these are Zener limiters. So these are Zener limiters, and you had it correct. It was a positive 8.2 volts at the peak of that part. Okay.
Where did we get the 8.2 from?
Okay, so we have 7.5, right?
Mm-hmm.
And then this one acts like a regular diode in this direction, which gives us what?
The 4.7.
All right, no.
Wait, what do you mean?
Okay, so
Or it'd
I'm
be,
giving
so
you-
if it acts like a regular diode, you're saying 0 or the 0.7?
0.7, right?
Okay,
Because now
okay.
our VZ is going to be VZ plus 0.7 for this first positive pulse. So VZ in this case, I gave you the values for VZ for each Zener, which VZ for this one is 7.5 and VZ for the other one is 4.7. But if it's running, if current is flowing in forward bias, we just ignore what VZ is, and it's just going to be 0.7.
Okay, that makes sense.
Okay, so what about the second part here? What are we going to be doing on the second part?
Would we just flip the rules? If it's negative on top, positive on bottom, it'd be a negative 8.2? Because
Okay.
in the bottom one acts like a bottom acts like a normal diode, and the top one's in reverse bias.
I mean, that sounds good and everything, but no. So let's look at this. So we have negative up here now, positive down here, right? So that negative is felt over here. Which Zener diode is in reverse bias right now?
The top one.
The top one, okay? So whatever VZ is, which in this case is 4.7, right? Don't we have 4.7 here? That's what our VZ
Yes.
is.
Mhm.
The other diode is doing what? Is that forward or reverse bias?
Forward bias.
Forward bias, because current is flowing this way right now, right?
Mm-hmm.
So if it's forward bias, what's our output voltage going to be on this last part, this last half cycle here?
It is going to be 5.3
Uh,
or
No. Close. Anybody else? I think somebody else started to say it.
Would it be -4?
No, not -4.
No, -5.4. Yeah.
Perfect. -5.4. -5.4 volts. Because here we have our negative VZ minus our 0.7 volts, right? Because this one is now forward biased. I mean, reverse bias. So that's 4.7. And then our anode, of course, is tied to the ground. So this is in the negative region, as you can see anyway over here. So we know we're going to have a negative value. So in this case, we have that -5.4 volts. Does anybody not see this before we go to the next example?
Nope.
Excellent. All right, so let's look at the next one real quick. Okay. So put in the chat box what your values would be for the first positive cycle coming through and then the negative cycle coming through. Let's see what you come up with. Theo, perfect. Nice work. Brett, perfect. You guys are getting it. Awesome. Keep it going. Good job. Okay, test, double check your, you got the V outs, the first part, right number, but the wrong polarity, and the negative side, that number is wrong. So check that again, check the V out again that you have. Martin, perfect. Good job. Nicely done. Yes, perfect. You got it. Good job. All right, anybody struggling? Anybody have any problems with this?
I'm just doing the math for it, that's all.
Okay. Tess, I'm not sure what that is. Is that Latin? I'm not sure. Oh, your cat got it right. Good job. Okay, no problem. Okay, so let's look at this real quick. We got one more to do and then we'll be done. So let's check it. Let's look at this. The first thing we have is our positive pulse coming in. Positive, negative. Positive over here, negative over here. Which one of these diodes are in reverse bias? Who can tell me which diode is in reverse bias?
12-volt one?
The 12-volt one. Okay, so that's the direction our current's going to go, correct? So that means our current is going to be going down. So if that one's 12 volts, then the other one is how much? How much voltage drop do we have across it?
0.7.
0.7. So on this first positive peak, we come up here, we have the 12 plus the 0.7. 12.7 volts, right?
Yes.
Okay. Then what's the bottom one going to be?
The bottom one will be the 5.6 minus the 0.7.
What do you come up with?
Come with 4 point.
No.
No, negative.
Okay. Negative what?
Negative 4.9.
Nope. You got the 5.6, right?
Mm-hmm.
And then you also have a 0.7. So
Hmm.
the negative VZ minus the 0.7, what do you get?
Negative 4.9.
No, put that in your calculator. Negative
Do-
VZ minus
Mm.
0.07. I mean minus 0.7.
Negative 6.3.
All right.
Okay.
6.3 volts.
Okay, I was confusing myself. Okay, you had to put the make it negative. Okay.
Yes. So it's just like adding them up, but it's just a negative.
Yeah, okay. Yeah, that's what I was doing wrong. That's why I was getting it wrong. So okay.
Okay. All right. So one more real quick one here. Let's see what you can do with this. Okay. What is our output voltage is going to be for the positive cycle and the negative cycle?
For the positive cycle, would it be 8.2, 8.2?
Look at the configuration again. Okay, Brett, those are perfect, except that you forgot a polarity on something just to make, there we go. Good job, Brett. Okay, we just have one Zener diode in this circuit, right? So when we have our positive pulse coming in, we have our positive here, negative's already down there. Is the Zener in reverse or forward bias? Theo, that is perfect.
Forward.
We have a positive here. This is a negative. Is that forward or reverse?
Reverse.
Reverse bias, right? So if it's reverse bias, then that's the only diode we have. Where's it going to stop clip off at?
At the 7.5.
Perfect. 7.5. So our here is going to be the positive 7.5 because we don't have another Zener in there that's, that's facing the other way to add another 0.7 to it.
Oh, okay.
Okay, so now we go through on the next side. We have our negative coming through. We have our negative up here, positive down here. What's going to be our output on that other half of the cycle?
Negative 7.5? No,
Is
no.
it in
no.
forward bias or reverse bias?
Forward now?
It's forward. So how much does a forward bias Zener's drop?
Oh, 0.7. Okay.
0.7. So here we have our negative 0.7.
Oh, okay.
Okay. So just remember that you need to look at the configuration. If we have one Zener, we know we're going to just have that 0.7 on the forward bias. And then whatever the value of VZ is for the output on the other side.